Welcome everyone to IE 342 Quality Control, and today inshallah we'll talk about Chapter 5, how SPC work, the Statistical Process Control works. We will go over the 7 main tools in the SPC. We will talk about them. We have already talked about them in Chapter 2, in Chapter 1, and today we will have a narrow down and scope about each one of them and have examples. As we said, the heavy of this course, quality control, is relying on the quality control charts. And today we will talk a little bit about the quality control charts or the control charts in this chapter, as well as the other 6 tools in the SPC. What are those 7 tools in the SPC? Those are the histogram or stem and leaf plot, which we already covered, the check sheet. This is new, maybe we have not covered it yet. The Pareto chart, we already talked about it. We will go over it again. Cause and effect diagram, and we will see how we can do it on the mini tab. Defect concentration diagram, this is a new one. Scatter diagram, and control chart. We will not go with this order, but those we will be covering during this chapter to prepare you for chapter 6 and 7, whereas the scope of each type of control chart and the numerical calculation will be started on the next chapter. So what is the control charts? The control charts are basically, as you see it here, it is a drawing, shows a plot of readings within a boundaries. Those boundaries, we call them the control limits. The control limits. This is the upper control limit, and this is the lower control limit, and this is the center line. Those are the boundaries of the control charts, and every control chart, regardless of the type or the name of that control chart, whether for continuous or attribute data, it will contain the same boundaries: upper control, lower control, and center line. The points here, you see them plotted on the control charts, are the data measured for the quality characteristics you are monitoring in the process. Those points has to be inside the control limits, between the lower and the upper. So we can say the process is in control. If the readings are exceeding the upper control limits or the lower control limits, in that time, we call that process is out of control and correction needed to fix the process. When the process is in control, there is a variation like what you see here. This is considered to be a common causes of variation, or they call it a chance causes of variation. So the chance causes of variation is when the process is in control, because all points are inside the control limits. However, if points are exceeding the control limits, then at that time we call that a special cause or assignable causes of the process, or the presence of the assignable causes or special causes, and that means the process is out of control. And in that case, investigation and correction is needed to eliminate the special cause or the assignable cause. The assignable or special causes is when the process is out of control. The chance causes or the common causes of variation, those when the process is within the control limits. It says always there is a connection between the control charts and the hypothesis testing. You have covered the hypothesis testing, I believe, in either statistics course or design of experiment. the hypothesis testing and control charts, they link together when the process is plotting within the control limits considered to be is equivalent to failing to reject the hypothesis of the statistical control. That means the process, there is no significance in the process. When the process, if the plotting is out of control, there is points is beyond the control limits, then we call that is equivalent to rejecting the hypothesis of statistical control. That means there is a significance in the measurements. That's why the relation, or there is a connection between control charts and hypothesis testing. This is very important slide, and all of these information are a foundation or basic information about the control charts in general. Why we use the control charts commonly, and it is very widely to be used, and it is very popular. The reason, those are not limited, but the main reason, we can say that the control charts is ensuring or assuring the process stability. The process stability means that the process can produce better. That means it can be improved. Their productivity, since it is stable, there is no ups and downs in the process. When the process is stable, we can predict the defect and reduce downtime or failure by detecting the defect before it happens and prevent the failure before it happens. Also, when we call that it is improved stability of the process, because it will prevent from changing the process often to adjust it. So the process, when it's stable, there is no need to change it a lot to make changes, as long as it is stable and it is productive and it is efficient. The control charts also provide a diagnostic. It is like when you do examination in the hospital to diagnose your body, your internal body organs. You do blood tests, you do other tests. This is similar to what we do as a human in terms of our body. The control chart is diagnosing the process visually and statistically. And the last one is to provide information about the process capability, to say whether the process is capable to meet the specification or meet the requirements, or if the process is not capable. The most important use for the control chart is to improve the process. As we said, also to stabilize the process and reduce variation, because most of the process don't operate in the statistical or in a state of statistical control. That means not all the process, or we can say most of them, they perform statistically. They are not in control, and they need to be monitored to make sure whether they are in control or they need to be in control if they are not, to do any changes or modification in the process, so you can put it in the control. So what that leads us to the use of control charts will identify the assignable causes. The assignable causes, as we said, those the reasons of having some plots out of control limits. That's what is the assignable causes. So we find the root of the causes, and we eliminate it to improve the process and put it back again in control. How we do that? We detect the assignable causes in this small diagram. It shows how it does. The input, and there is a process, and there is an output. The measurement system, or where is the control chart, it falls here in the middle, whereas when the process is running. To detect any assignable causes, if there is any assignable causes, then you have to identify what is the root of that cause of that problem, and then you implement a corrective action to fix it, and then verify if it is fixed or no, and then you keep monitoring the system until there is another assignable causes found. The Shewhart control charts model, this is the general model used for all type of control charts, but then depend on the type or the control chart's name, whether X bar R or P chart or C chart or U chart, which we will study inshallah in the coming chapters, then we can adjust this method to fit the need or to fit the type of the data. Here, this is the general model. As we said, all control charts contain of control limits, upper control limits, lower control limits, and center line. The center line always identified as the mu, and the upper control limit is the mu plus L standard deviation. The W here is referring to the quality characteristics that you are measuring or you are monitoring. For example, you are monitoring the dimension of the product, you are monitoring the quality of the reliability of the product. So the W will refer to the dimension if it's height, or if it is a weight, or if it's a temperature, or if it is number of scratches on the product. You can name it any quality characteristics you identified in the product or in the process, even if it's a service process, that considered to be a W. Mu, I think all of you now know it is the mean. L multiplied with the standard deviation. What is the L? L is the distance. You can, so you don't forget the abbreviation. Instead of distance, you can refer it as length. It is the distance from the center line to the control limits. The distance of the control limits from the center line. Now we are in the upper control limits, so it is the distance between the control limits, the upper control limits, and the center line, which is the mu. The lower control limit is the distance, the L refers to the distance between the lower control limits and the mu. The L multiplied with the standard deviation, and that's how we measure the distance in the distribution or in the control chart, similar to the normal distribution. We measure it by the number of standard deviation. 1 standard deviation, or 1 sigma, 2 sigma, or 3 sigma from the mean. And that is what it refers here as the control charts model or the Shewhart control charts model. This is the general model, which was founded early after World War II, and then it was modified, or it was the root to develop all the type of control charts that we will discover them in chapter 6 and 7. How the control charts work, we saw the control charts figure before, and this is similar to that one. The center line, again, upper control limits, readings. This shows the difference when you use all the measurements, the individual measurements. See how the distribution is relaxed here, and see how it is tight. This is when you use the X bar, which means the average of the data when you use the center limit theory. We will talk more in depth about the X bar, inshallah, in the coming chapter. But this is to show you, if you go with individual readings, every reading you collect, you do it, it will give you a shape similar to that one. Compared when you have the center limit theory, it will normalize the data more, so you can track the averages of the data instead of every reading. And that will depend on the type of data that you will collect. And then from there, we can decide which control charts we can use. Also depend on the sample size of the, along with the type of data, the sample size. It is one of the metric to determine which one is going to be used. About the sampling, since we talked just about the sample, you may find in some slides of this chapter, and uploaded, slides. Some slides talked about the sampling, where is the average run length. And in that case, you don't really need to focus here about the sampling, since we are going to talk in detail about it, inshallah, in later chapter, if we have, inshallah, complete this course on time. I usually have extra material for quality control that benefit you, and it is within the content of the course, and one of them is the sampling along with the QFD, quality function deployment. So you don't have to go over that one when you study for chapter 5. We focus on the 7 main tools, the control charts model, and what we are going to cover here about the control charts, along with the other 6 other tools. More basic principles here about the control charts. It will be discussed and investigated in chapter 6 when we talk about the variable control charts, that is based on a variable data like continuous data, like temperature, like length, height, or when we use attribute data, then we will study the control charts for attribute in chapter 7, like number of counts, number of defects. Then it will have a different type of control charts. The control chart design, it's encompass a selection of sample size, control limits, and sampling frequency. And this is what I was referring to. The control chart design, it will be working along with those things, as well as the type of data, whether it is a variable or a variable or attribute. The control limits formula, it will also based on the type of control chart we are going to use. We have just covered the main formula or the main model, and then we will study each formula for every different type of control chart. The sample size, it will be another thing that it will be considered in designing the control chart, as well as the sampling frequency. The type of process variability, this is very important, and this is one of the things that always to be questioned for students. What are the types of process variability? What is variability? First, variability is change in the values that appear when you do or conduct a control charts. We see here different type of variability. All of them, they are common between, the common thing between them, they are all having variability. The different is the type of the variability. We have 3 types of variability, or we can first divide them to 2 types, and then one of them, it has another branches. The 2 types are the stationary and the non-stationary. The stationary, like here, figure A and B, this is considered to be stationary type of process variability. This is the non-stationary. Stationary mean, what does it mean, the stationary? It is something that like coming from the word station. So it has like a state, fixed, whether it is ups or down, or the trend or the type. The non-stationary is something like random. It doesn't have any sense of stability. In terms of the stability, in terms of the shape, but all of them, they are variability. We all agree those, all of them, they have variability. What is the stationary? The stationary has also 2 types. The stationary with the uncorrelated, like A, the stationary with the autocorrelated. What is the uncorrelated and what is the autocorrelated? The uncorrelated, this is the commonly seen. Also B, A and B, those are the commonly seen. The stationary uncorrelated, that's when the data vary around a fixed mean. So the fixed mean, you can tell it is here in the middle, and the data are just ups and down along or around the mean. You see how They are look around the fixed mean, and they are stable and predictable manner, because you can see them. If you continue with this chart, you will see again it will continue in the same manner. It is predicted. The other type of variability is the, and under the stationary, is the autocorrelated. The difference in the autocorrelated, this stability, it doesn't appear only in the one side, or let's say it is not appearing in the same trend or the same pattern around the mean. This changes appear either above or down the center line. As you can see here, you can see the trend of the variability. It appears here above the mean, and then the variability again, it is appearing under the mean, and here is upper or above the mean, and then it will go down under the mean. So it is successive متتالية observations. So data successively are dependent with the tendency. Tendency معناها تميل إلى to move long runs، يعني قراءات كثيرة on either side of the mean. See, this is either, this is one side اللي هو upper, or another side of the mean which is the lower. So it is similar to like say cycles, but it is kind of also stationary because it is predicted. You can tell that it will go up again or it will go down again. Here it will show you more stability or more predicted because it is always around the mean. There is no successive point above or successive point below. The non-stationary is the one that doesn't have any sense in terms of how the process works. The process drifts, as they mention here. Drifts معناها when you do drifting, like you are moving without any stability in the direction. So the direction here, you can see it is going up, and then just for the sudden it drops all the way down. Then it keeps under the mean, even if it's increasing, but it's also under the mean, and then it goes down again under the mean. So there is no sense of the movement, or there is no fixed also mean, because the mean usually it is applied here in the middle. So you tell that the data, it is around it. But here, when you draw the mean, you see cycles goes ups and down the mean, or also ups or above the mean without any trend, without any prediction. Here, either up or down. But here it can goes up and then increase up, and also it can goes down and increase down and do some cycles below the mean. So those are the types of process variability. It is very important, and you need to know the difference between them. The choice of control limits, usually here we will work with the, in this course, we will deal with the typical 3 sigma control limits. That is based on the probability of the majority of the data, which is above 99%, or the probability of having data beyond the 3 sigma limit is 0.0027. This is based on the statistical Z table that you have covered in statistics course. So we are working with the 3 sigma control limits. Those considered to be the control limits. However, it is very important to know that what is the warning limits. The warning limits, that mean you have to pay attention to your process, and that mean it is the 2 sigma. The 2 sigma, it is giving you the identification or the warning that wake up, your process is going now close to the control limits. If most of the readings going next to the 2 sigma or exceeding the 2 sigma, so you are getting close to the control limits. So it is important that we are working with the 3 sigma control limits, and that's lead to the probability of having data beyond the 3 sigma with only 0.0027%. This is the probability that the data will be out of the 3 sigma. This is based on the normal distribution Z table. And we have to know that the warning limits are the 2 sigma limits, or the 2 sigma. As we said, the sampling size and frequency, it will be covered later, inshallah, in the future chapters. Those only just to show you there is a formula called the average run length, which will really give you the, if you are using a 3 sigma control chart, let's state the formula here. ARL, it is the average run length, equal 1 divided by P. The P is the probability of exceeding the control limits, the probability of any points that exceeding the control limits in the control chart. And what it does really calculate, it calculates the number of points before the first out of control will appear. So when you divide 1 over the probability of point exceeding the control limits, then it will give you the number of points before incidence of control out of control will appear. So if we use the probability from the previous slide, the 0.0027, which is the probability of having defect beyond the 3 sigma limits, if we use it here and we divide 1 over the 0.0027, it will give us 370. That's mean it will need or generate 370 samples before out of control event will appear. This is just for information. More than will be discussed about the sampling in the future chapters. This is the important part, this slide and this one. In these 2 slides, you have to pay attention. As we said, if the point exceeding the control limits, that means the process is out of control. Some references in the quality, after studying the control charts for years, they have listed some patterns and events where out of control also can be appear and correction is needed. So as the point, if it's exceed the upper control limits, there are some events. Those event is very specifically, and it is written here in a way very specific. When it happens, you have to investigate in the process. You have to investigate in the process. The first one is the one that we have said and talked about, which is the 1-point plot outside the 3 sigma control limits. The upper control, lower control. If there is a point exceed them, then this is out of control. We all agreed about. The second one is 2 out of 3 consecutive points plot beyond the 2 sigma warning limits. We talked about the warning, and we said the warning, that's mean if your data is exceeding the 2 sigma, then there is something is going to be close to be out of control. So this rule says if 2 out of 3 consecutive, what does it mean? 3 نقاط متتالية. 2 of them are beyond the 2 sigma level. Where is the 2 sigma? We call it zone A, here after the 2 sigma. Zone C is the center line and the 1 sigma. Zone B is the 1 sigma and the 2 sigma. Zone A is the 2 sigma, and which is the zone between 2 sigma and the 3 sigma. The out of control that is beyond the upper control limits, that means beyond the zones, whether A or B or C. But here, point number 2 says 2 out of 3 points. These, for example, 1, 2, 3 points. 1, 2, 3 points. So if 2 out of 3, but those are not representing number 2, but those are 3 points consecutive. 2 out of them let's say the last two, they were on zone A, then there is also an event for out of control and needs to be investigated. The third one is 4 out of 5 consecutive points plot at a distance of 1 sigma or beyond from the center line. What does it mean? It means that here 4 out of 5, we have 1, 2, 3, 4, 5. Those 4 points are either at 1 sigma or above. See what is the rule says? 4 out of 5. 4 من 5. Consecutive متتالية. Plot يعني اترسمت at a distance يعني على بعد of 1 sigma or beyond. Of 1 sigma or beyond. يعني if it placed here, consider to be 1 sigma. If it's placed here, also it is 1 sigma. Okay? So it is 1 sigma, sorry, here, if it is here and up, this is 1 sigma, and from here and up, this is 2 sigma, and here is the 3 sigma level, and this is the upper control limits is beyond the 3 sigma. So if it is here on zone B or above, these are 5 points. 4 of them, it has to be consecutive. It has to be consecutive. That's mean either this from the starting point or from the end point, because it says out of 5. And it has to be, you have to collect 5 points, 4 of them consecutive. They are what? Either at 1 sigma or beyond. Okay? At 1 sigma or beyond. The number 4 rule, 8 consecutive points plot on one side of the center line. So you count 1, 2, and then if we consider this is 3 also far, 4, 5, 6, 7, 8. If all of those 8 were above the center line, or below the center line, then you have to investigate also in the process if something is happening. This is based on the Western Electric Handbook. It is very famous. You can search it. It was, as you can see, published in 1956. And there are other references that is developed more than those 4 points from Western Electric that consider the 4 Western Electric rules, and they added another 6 points, like here number 5, 6 points in a row, steadily increasing or decreasing. That's mean either the 6 point is having a trend to up or trend down. Number 6, 15 points in a row in zone C. That's mean 15 consecutive point. Consecutive is equal to in a row. So if you see in a row, it is equal to consecutive points. متتالي. Are in zone C, and here is zone C. Between the center line and the 1 sigma, if you have 15 points in this zone only, after each other, those 15 points, that's also another sensing that there is something in the process need to be investigated. 14 points in a row, alternating up and down. That's mean you have 14 points in the control chart, like from here 1, 2, 3, 4, 5, 6, 7, 8, going to up and then going down or continuing ups and down. 8 points in a row on both sides of the center line within none, with none in zone C. That's mean those 8 points not only in above the center line or below the center line, but none of those points are in zone C. So all the points were in zone 8, zone B and zone A. An unusual or a non-random pattern in the data, and this is referring to number 9, referring to here, referring to this type of unnatural variability, like the one here in the C, that is non-stationary, because those are predicted unless if one of those has breaking one of the rules or meet one of the rules here. The last one or more points near a warning or control limits. And this is close to number 1. So number 10 is close to number 1. Those points are very important, and you have to know them, and you have to know how to identify them in the control charts. I can bring more example of charts where it contains some points, like example from 1 to 10. Basically 9 and 10, it is similar to other points. So for the majority or the common are the first 4 points, as well as those are also important. So I can bring more samples so you can see and know how to identify them, but it is very important to know those rules. As the softwares now, they can identify them automatically, and they can generate in the report those causes of variability, and tell you that it is 14 points in a row, or it gives you a code means that it's a 14 points in a row, alternating up or down. But also, as a specialist in industrial engineer field, you have to know what is the difference between them and how to identify them. And they are very only limited situations, so you have to know them as a part of this chapter material. Phase 1 and phase 2 of control chart application. Usually phase 1 is to correct the process and put it in control after it was out of control, and we call that retrospective analysis, or we call it phase 1. And in that case, the charts are effective to detecting large sustained shifts in a process parameters, outliers, measurements, errors, and all that. Phase 2, usually the process is more stable, and now the process to be monitored, not on bringing natural process readings. So in the phase 1, the process usually, as in the measure phase of the make, when we recall, you measure the, or you use the control charts, you will find the process variability is high, there is outliers, which is out of controls. Maybe the process even is not capable. But phase 2, after you do the improvement needed in the process, then phase 2 in the control chart application, that comes in the control phase of the make. So in that phase, you monitor your improvement and you expect the process more stable. We will continue with now the other, they call it the Magnificent 7, which is the 7 SPC tools. We have covered now the control chart. We will cover some others today, and the remaining we will continue it in the next lecture. The first tool, which is the check sheet. The check sheet is very common and it is very simple, and maybe I can give you an example where it can be used, and you all see them when you go to a mall or a hotel and you enter عزكم الله, the restroom. You see a check sheet always close to the door, where it states the cleaning checks, whether that restroom being cleaned and the time. You see some checks, some signatures. This is similar to the check sheet. The check sheet is also, you can refer it when you go and do your car maintenance. You see the technician has a check sheet, give it to you at the end, where they check regular checkpoints in the car, regardless of the type of maintenance you are doing. They do check the tires pressure, they do check fluids, they do check the battery of your car, brakes. Those are, they have a routine check, so they develop a check sheet, so you don't forget those things need to be done. This check sheet can goes to different type of information that based on what it needed. There is an example here for operation, and it shows the variation here. It comes from one of those things that need to be considered or reported when the errors happen from them. If there is electrode failure, they have to check, and they write or type down what is the error, what is the description, and what is the action needed. You can see that also in the troubleshooting manual, where it shows you all these list of errors that could happen, and what is the code it will enter or it will appear in your screen, and what is the description, what action needed to do. For example, like the engine check light, it could appear, and then you have to read the type of code, because that it could be different issues. It could be coming from oil level, or it could be maintenance due date, or sometimes even just the gas tank was not tightened enough, so the check engine light, it goes up. So they have list of checkpoints and errors, description, action, or it can be something simple like this one here. This is the defect type, or the defect based on the month in the year from 1 to 12. And then what is the defect was, for example, parts damaged, how many of them in month 2? They were 1 only, 3 in April, 1 on May, processing out of order, it was 2 in January, and so on. So you can have a tracking for a check sheet. It's something that doesn't need a software application. You can develop it based on the process or your application. It helps you to collect data, and then you can analyze them statistically. That's why it falls under SPC. The other one is the cause and effect that we covered it in the remake. And today I will show you on the mini tab how you can develop the cause and effect diagram using mini tab. So I will share the screen now with you and open the mini tab. So please open in the mini tab and try to use or do the same example. So let's share the screen. Okay, here is the example. Basically, you put the cause and effect categories first on the main row here, on the gray row, on the mini tab sheet. The categories, as we said in the chapter 1, those categories can be different based on your application, but those are very common in process to have measurements, type of causes, material type of causes, personnel means human, machines or methods, that means system or so on, environment. Those could be the categories of the causes. The effect usually written here or identified by the customer. How we develop this chart: when you develop the main causes categories here, after you develop, for example, the man, which is the personnel, the machine, material, method, measure, then we have an extra here after the environment. This is environment. We have training, speed, micrometers. Training, speed, micrometers, those are not major categories. Those are subcategories under the main categories here. For example, the accuracy and condition, it falls under the measurement. So under the measurement, under the micrometers causes, the condition and the accuracy are another root of causes for the failure or for the effect of the failure. The speed, which is the too slow or erratic, that is a branch of the speed cause that is under the machine. So we have the machine, we have 4 types of causes under the major cause, which is the machine. Under speed, we have either too slow or erratic as a branch from speed. For the method, we have angle, brake, end gear, environment, we have moisture percentage and condensation. All these are causes under the main category, whether the environment or method. But some categories, and this can be applied to others, they have branched under their causes. For example, the speed, it has another causes for that one. So it can be, or it has to be identified in different rows. When you develop this chart, you go to quality tools under stat. You go to stat, quality tools, cause and effect diagram. Here you can write the effect that is developed by the customers, and it will appear. So we can say defect increasement, and in the column you choose the causes category or causes main categories. For example, here we have the man, which represent the personnel. You can change those. Those are identified by Minitab, but you can change them if you want. You can change those based on your application. Those are the common, but you can change them. Those are labels. Here are the data where it is collected from. So you select the data from C1. So C1 is here, the column of C1T. That is where is the data, and you press to have the data for the personnel. For the machine, you also go for C2, you go for C3, for the material, and so on. But if you have, for example, like what we saw there, for the machine, there is a sub-causes under the speed. So what we do, we go to the machines and we press on sub here on the right, and when it opens, it will show you all the labels you identified already from your data that was under machine: sockets, bytes, lattice, and speed. You see them here, and you select where is the data you want to add for the sub, whether the sockets or whatever data here you have. You have a branch of that next to it, so then you select it from the rows here. And in this case, we have C8, which is speed, under the label speed as a sub causes. Then you press OK. You do the same for the machines. I think machines, we have another sub. Yeah, this was the machine. So let's go for the What else we have here? We have instruments, so let's go for measurements. We have the micrometers. It has a sub of causes, which is the accuracy and condition. Again, you select the data from C9 to put it here by pressing on C9, so it will appear here. And then OK. After you press OK, it will demonstrate the chart to you. And here you can see now when we wrote the effect, which was driven from the voice of customer, you can see it in the graph. Then you can save the graph, save it, print it, or edit it, or you can change it as you like. And here you can adjust the data as your application needed. That was for the cause and effect diagram. We will continue with another tool of the 7 tools of SPC. This is another example of cause and effect diagram. And you can see the machines, material. You can try this example here. Try to do it on the cause and effect on Minitab, so you can see how you can develop cause and effect diagram on Minitab. You can see here sub-branches under for example, the personnel. There is sub-branches. You can have them and try to draw this figure. What else here? Yeah, this is one of the examples. This is another example here. Also, you can try it at home to see how you can develop the chart. Here, the categories are different. They are not material measurements. You can see different material because it depends on the application. Those are common categories, but every application will have their own categories or their own criteria. The other tool is the scatter diagram. The scatter diagram is also being covered in chapter 1, and also we can do it on the Minitab. I will share the screen with you to show you an example of it shows usually the correlation between data, as I will show you now here in the example. Okay. Here is the example of the scatter diagram. The data was a temperature versus the ice cream sales. This can be an example brought from ice cream store or ice cream shop when they would like to measure their sales number compared to the temperature in the city or at noon time. So when the temperature is increasing of the noon at noon time at 12 noon or 1 afternoon, the sales is increasing because people would like to cool down using ice cream. So how to do a scatter diagram? Basically, you go to graph. It is the first plot, scatter plot. Then use the simple, or you can use other type, depend on your application. But here we just cover the simple, and maybe in the other like design of experiment, you can use the one with the regression. You choose the data for the y-axis, the x-axis, and then you press OK, and then the diagram will be plotted automatically to you to see the correlation. That shows you how the relation it is between the variable, and it helps also in terms of statistics because you are collecting, measuring data, and then you analyze them using this tool. That is why it is one of the famous tools in SPC, one of the 7 magnificent, as they call them, tools. I will stop here and we will continue with the more tools remaining on the next lecture, and I will open now the time for the questions.